So hi, everyone. I always loved hearing other people introduce me because I always get kind of a new, bigger ego, you know. Anyway, my name is Kurtzer. I am the HPC Systems Architect for LBL, the IT department within LBL. And I've done some open source work, as was mentioned, and various projects in CentOS and Werewolf. But today I'm going to talk to you about Singularity. So Singularity is a container solution. So just so I have an opportunity to meet everybody in the audience, show of hands, how many people here are service providers? People started raising their hands before I even said it. Just how many people are service providers? Okay, some form of compute, HPC or scientific compute, okay. What about users? How many users do we have? Okay, there's a lot of people that didn't raise their hands. I'll give you an opportunity. How many people know about containers and are familiar with containers? Okay. If you don't, that's fine, because I'll teach you right now. As a matter of fact, I'm going to take you through a brief introduction of containers. So in case you didn't know, this is a container, but it's a shipping container. It's not exactly kind of the containers that we utilize in science and in industry and enterprise. So this is a metaphor for what we're going to talk about. And if we were to describe a software container, we would say that it is a, well, there's a lot of definitions, and people will define this in a lot of different ways. But I'm going to go to the lowest common denominator that I could find, just to make sure we're all on the same page. And that is an encapsulation of an operating system environment. So I'm getting a little feedback. Is anybody else hearing that? Okay, I'll lower this just a little bit. Okay, I don't want to be guilty of any feedback loop. So containers are encapsulations, basically, of operating system environments. And even if you have different definitions for it, that's fine. But we're going to go, for my talk, because I'm talking, we're going to go with the least common denominator. So containers are the encapsulation and a means to use it. So going back to this metaphor, if we look at a shipping container, but we want to kind of talk about it as a software container, well, we're going to put some things into it. So for example, a Linux distribution. You can choose CentOS, Red Hat, Ubuntu, whatever it is you like, you put it into this container. And then you add other applications and whatnot onto it. In this case, we're looking at, we got a couple of web servers, some database servers and whatnot. So this is kind of a really good example of how the enterprise uses containers. And I'm going to talk for just a moment about how the enterprise uses containers, because that's where we get our understanding of what containers are. So in a nutshell, the enterprise uses containers and container technology for microservice virtualization. Anybody ever heard that term, microservice virtualization? A couple of us, but not many of us, I think, are in enterprise. So this is really an enterprise buzzword. Anyway, it's important to know. So if we were to look at what microservice virtualization looks like, again, using images as a metaphor, here's a Linux host. We know it's Linux because Tux is driving it, of course. So this is a Linux host, and it's not doing much. It's kind of empty. So if we were to take this metaphor, carry it to the next level, and say, well, how does containers apply to this, and specifically microservice virtualization type containers? Well, this is what enterprise and industry typically does. They take as many of these containers as they possibly can, and they'll put it on this one Linux host. And each one of these, because they're running microservice virtualization, and the whole idea of it is really isolation, they all appear like they have sole occupancy on that host. They're all sharing that host's resources. This works great for enterprise and enterprise apps, because enterprise apps are not very computationally intensive. For the most part, they're usually just sitting there, kind of idle. So you can get away with doing stuff like this. But it's really important to note that this is, well, actually, this is the next logical progression. And this is how enterprise, by the way, knows that they're now achieving really good utilization of their resources. You know, they go to the tipping point and they back off just a little bit and they say, yeah, we got full utilization of our facilities, of our resources and whatnot. So again, I want to mention, this is not the HPC or scientific computing use case. Do you all agree with me? Show of hands, yes? Okay, come on. This is not the use case that we are going for in scientific computing. As a matter of fact, our use case is kind of the opposite of this. So let's take a look at this metaphor again. So now, our use case, we saw the enterprise use case. So now this use case, it's kind of subtle, so you have to pay attention to it. This is our use case. You ready? Did you see it? So we have the whole ship. We've got this huge amount of resources, and we really just have like one container that we want to utilize that entire resource with. This is really different than what enterprise is doing, isn't it? So as a matter of fact, this isn't the only use case that we have. In some cases, we have use cases that are like, we have a whole bunch of distributed computing, and we want to basically take a whole bunch of containers and run it on a whole bunch of different types of systems and resources. So does anybody know what these are? It's not exactly quite as glamorous as they are in the movies, are they? These are pirates. And these are pirates pillaging resources. So yeah, modern day pirates pillaging resources. We don't have no Jack Sparrow anymore. It's that romantic idea is gone out with, well, still alive in Hollywood, I guess. But modern day pirates pillaging resources. So I'm gonna kind of go out there and say something. And I can say this because I'm a researcher too, and scientists are cool, and pirates are cool. So in a matter of speaking, scientists, we're kind of like pirates. Bear with me for a moment, because we're always looking for the next resources. We're always looking for more resources and more booty that we can pillage. But our booty's not gold and treasure and stuff. What we're looking for is resources, compute resources. And luckily, in this day and age, well, there's Jack Sparrow. But luckily, we can find these usually, because there's a lot of people offering them. Everything from cloud-based resources to centers that are providing it, groups that are providing these resources. So finding the resources is not really the biggest problem. But when you have all these different resources spread out all over the place, how are you going to guarantee compatibility with these resources? I mean, on each one of those resources, chances are you may have root, but chances are you're not going to have root. So how are you going to get all of your application stack and everything that you need installed onto those resources in a scalable way? And so this is where containers for science might be a perfect fit. Yeah, so as I mentioned, our use case is really different than enterprise. But let's go back real quick, because the most common question that I get since I've started doing this is another show of hands. I want an active participating audience. So Docker, who's heard of Docker? Okay, why is it more people have heard of Docker than apparently do work in here? I mean, okay, so what about Docker? What's going on with Docker? So Docker is the most well-known container platform, as we just kind of proved. And why is that? Docker is filling a niche, and it's a huge niche. It's microservice virtualization. And so many different groups and industries within enterprise have been utilizing Docker because it fits that model really, really well. Now, what else does it do? It facilitates creating, managing, copying, sharing your work with others, and it facilitates all this in a really good way. I mean, it's really good at that. It's kind of reproducible. It's kind of reproducible. It's mostly reproducible. I'm not going to say it's 100% reproducible, because those of you that are familiar with Docker know that each image is based on a whole bunch of layers, and your image is based on someone else's work, and their work's based on someone else's work. And they can change their work, and when you go to rebuild your image, you might be getting different bits. But it's mostly reproducible. It's easy to install. It's well documented. It's standardized. And for these reasons, scientists have kind of jumped on this bandwagon. So out of the people that are here, how many people actually use Docker? So there's a good amount of people here that use Docker. And I think it's fantastic, because Docker has filled a lot of the needs that we have as researchers. So why don't we just keep using Docker? Well, the good news is you can. I'm not up here to try to tell anyone what to do. I'm not your parents or PIs or anything. You do whatever gets your work done. That's the important thing, right? And you can definitely use it to share your work with other people and to make good use with it and leverage that workflow. But I will tell you, and if you don't already know this, you can either thank me or kick me later. It's up to you. I prefer the thanks, but It is a dead-end path if your goal is ever to get past local private resources, because there's not many HPC centers that will take the risk of running Docker. And this is because the usage model and the design of Docker is for microservice virtualization. And that model does not fit very well with high-performance computing infrastructures. So centers can't install it and provide a reasonable service to the users. Does anybody here know of a center running Docker on their traditional big HPC? Okay, not one. Good. Every now and then somebody raises their hand, and now I'm like, oh, God. Okay, so yes, that's the right answer. Nobody's actually doing this. People have tried. I know some sites that actually spent about 8 to 9 months of FTE, full FTE effort, trying to get Docker running on their HPC resources. Couldn't do it. Singularity came around, and they were able to do it in an hour. So sorry to that guy. Anyway, so again, I just want to reiterate, you can keep using Docker. I think it's a fantastic tool. But if your goal is to get onto bigger resources and to move around, you might be on a dead-end path. Anyone ever? Okay, so Singularity to the rescue. Come on, I thought this was really clever. Nobody else did? Okay, yeah, pictures now. All right, so Singularity to the rescue. We got it? Cool. Okay, so let's talk a little bit about Singularity. It's really developed from necessity. As I mentioned, scientists have been using Docker for a number of years now. I mean, it's been in the wild now for what, 3-4 years now. And my center, as well as other centers, I'm sure, have had scientists coming knock on your door and say, you know, I got this Docker thing installed, and it's really working well for me on my resources, and it was easy to install. Just throw it on the HPC system and you know, let us go to town with it. And you know, my site, like other people, said, no, we can't really do that. But the scientists, you know, they don't care about our problems. I mean, I'm sure you do, but you know, really when it comes down to it, you guys are trying to get your work done. We're trying to maintain a secure, compatible environment for not just you, but for everybody. And that's very difficult to do with Docker on the system. So we kept pushing them off, pushing the scientists off, saying, sorry, we can't do it. I've been bribed. That was cool, although it wasn't a big enough bribe, apparently. It could have been a lot better. But bribed, threats, demands, you know, scientists really did want this. And so I started looking at this problem in a lot more depth. And I came up with the idea of Singularity quite a while ago. And I started developing it. And in April 2016, had the first release of 1.0. Now, I'm going to ask for another show of hands. Everybody get ready, because this one's a big one. How many people heard of Singularity before coming here? Okay, about half. That's really cool. So now how many people have heard of Singularity? Okay, just checking. Okay, so the first public release in just 8 or 9 months ago. And in 8 or 9 months, out of a somewhat random pool of people, random, you know, HPC people, about half the people have heard of Singularity. So the growth and the uptake has been just phenomenal. It's been mind-boggling for me. The last time I saw growth like this, I will just be honest, was when we released CentOS. CentOS had uptake like this. So hopefully I'm as optimistic of where Singularity will go, although our niche case, our use case is much smaller than what CentOS is. So I'm hopeful. Anyway, once I created and founded this and released it, a whole bunch of people started joining up and helping. And the project has grown substantially. And now I can honestly say it's created, you know, for the people, by the people, well, for the scientists, by the scientists, you know, something like that. So, and that's really important because we are now bridging the gaps between the end users, between the resource providers, between operating system developers, and all these different groups. And we're actually coming up with a solution that's specific to enable science. I think that's really cool. As we've matured, we've gotten tighter integration with other scientific applications. Nextflow, Slurm, MPI. By the way, MPI is not bolded with those. It's wildcards. It's because every MPI that I know now has talked to me and trying to get integration with Singularity. Everything from Intel MPI to MPitch, MVAPitch, OpenMPI. You name it. I've now talked to most of the MPI developers, the various MPI developers, or somebody from their teams in terms of getting Singularity working with it. And I'll show an MPI example in just a little bit. We also have integration with other container technologies. As you could see, people are using Docker. And there's actually much more percentage of scientists using Docker, in my at least perspective, than what was represented even in this room. It's a lot of researchers using Docker. And if we're going to offer another container platform, we have to leverage that use case and all of those people doing this. We don't want to leave them hanging on a dead-end path. We have to basically make a bridge and come up with a solution. Let's see. Also gotten various awards. Now, this has been mind-boggling for me. The awards, the articles, the presentations, other people picking up on this and whatnot, and interviews. I'm being interviewed. That's kind of weird. I don't know. It's kind of weird. I'm always self-conscious about interviews, but I'm getting interviewed, and it's cool and weird, I guess. But HPC Wire Editor's Choice Award for Top Technology to Watch in 2017. Just to give a scope of the other types of projects that got this. TensorFlow, Google's TensorFlow. Big project, a lot of resources behind it. NVIDIA's DGX platform. A lot of money, big project behind it. Large, significant impact to scientific computing, both of these. And this little project, Singularity, got unanimous votes from the HPC Wire team that this is a top technology to watch in 2017. So that's very cool stuff. Let's talk a little bit about the design goals. It was architected from the ground up to support mobility of compute, computing agility, bring your own environment, portability. These are all words to basically describe the same thing, extreme portability. This means that you could take your container image and carry it with you. And you can do this. Let's say you build your environment. It has all of the scientific apps and tools and whatnot that you need inside that environment. And you can carry it with you from system to system, cloud resource, host, doesn't matter. As long as Singularity is installed in that endpoint, you can always work in the environment that you have created. That's very powerful. One of the things that enable this is the fact that we're using single file-based images. Now, Docker, again, I'm going to go back to the Docker model because a lot of people are very comfortable and familiar with it, uses layers, as I alluded to. And these layers are not always the easiest thing to recapitulate on different hosts unless you put it up into Docker Hub, which is completely public. And that works for a lot of people, but it doesn't work for all of our scientific use cases. There's a lot of controlled software and whatnot as well that we have to be aware of and manage that, as well as commercial software that you may not want to put publicly up into Docker Hub or something along those lines. But having a single image, there's some really cool effects of that. For example, copying it over to a system is just like SCP or grid FTP or rsync. You can just copy it to wherever host you're going. You can archive it, you can compress it, and you can upload it into Google Drive because those in academia, sorry if you're not in academia, have things like unlimited Google Drive in in the Google Apps Suite. So you can just upload as many as you want there and pull them down from wherever host you want. But it's really efficient. Oh, there's one other aspect I do want to mention, which is sharing. Sharing your container now is easy as changing the file system permissions on your image to give someone else read-only access to it. And then someone else can spin up a Singularity container simply by just pointing it at that image. And they can now use that environment. But also, this is extraordinarily efficient for parallel file systems. Anybody here use a parallel file system in some way, shape, or form? Yeah, I hope so. Well, the image is one file. It's one metadata call to your metadata server. So it doesn't matter if you're starting up a very I/O-intensive application from within your container. PyMPI comes to mind. A lot of people are using that. But that's incredibly difficult for a parallel file system to deal with. But with this inside of a container image specifically, it doesn't matter how many internal metadata operations you're doing inside the container. It's only one hit to your metadata server. It's really, really efficient. So moving on. It's important that we don't have any architectural or system changes to make to your cluster in order to make Singularity work on it. So this means that it is a single application to install, configure, make, install. And you're pretty much done. A system administrator may want to edit the configuration file and tune it for a particular host, but for the most part, that's all there is to it. And then users can basically go to town. One of the reasons why it's so easy to deal with is because we limit the user access. So if a user is a user on the outside of the container, which usually they are, when they start up Singularity, they're going to be the same user inside the container. And this is a really important component to it, because if you're the same user inside the container as you were outside the container, well, the whole idea of security and isolation of that container, you can kind of start dropping some of those walls between isolation of what is inside the container, and you can blend the line between what is in the container and what is on the host. And now you could use the host's resources directly from within your container. I hope that makes sense to people. I'm going to show some examples in just a moment. There's also no root-owned container daemon. Docker, for one, has a root-owned container daemon. I can talk about this stuff, by the way, for about 2 weeks straight. So I'm going to try to, I keep finding myself trying to curb myself a little bit. But there's no root-owned container daemon. And just to really quickly explain this, why this is a big deal. If you imagine there's a Docker daemon running, and for a user to control or bring up a container, a user has to make a socket connection to the Docker daemon. And they do that. And the Docker daemon then spins up a container on their behalf and will run code inside that container, again, on the user's behalf. And it runs it by default as root within the container. Now, if you can imagine the security implications of that, but for the moment, let's just talk about the resource manager. The resource manager is another root-owned daemon sitting on the nodes. And as soon as a user schedules a job, and the resource manager basically allocates that job for the user, well, that job can say, well, I want Docker to spin up a container for me and run a job. So inside that job script, the Docker command contacts the Docker daemon and runs the job. Now, the Docker daemon's running the job on their behalf. There's no process execution pathway that is linear. It kind of escapes the realm of the resource manager, because now that command, that Docker command inside the resource manager job script can actually detach, or it can close, and the container is still running. There's no way for the resource manager to actually now interface directly to the Docker daemon. There's some efforts to try to do that, but so far they've been not the best ever so far. Maybe in the future someone will get there. But at the moment, it's a very difficult problem to solve. And then as soon as you start talking about doing MPI and coordination between multiple containers, oh my God, the complexity just went up by like 2 to 3 orders of magnitude. All right, so moving on. Another design goal was simple integration, absolutely simple integration with things like resource managers, InfiniBand, MPI, GPUs, file systems. It even supports multiple architectures. We have it working on ARM and PPC 64. Okay, so let's give an overview of Singularity. Now, I'm going to go back to the security the security model, access permissions, because this is a really big component of it, obviously. This is what stops so much HPC centers from running Docker. So again, a user running a Singularity container. User X is going to be user X inside the container. But Singularity is going to take this a step further. Singularity is actually going to block within the container any ability for that user to increase their own privilege. So here's a very simple use case. I have a container. I built it on my own system. And I know root's password. Ha ha ha! I bring this onto the supercluster or to a cluster and spin up a Singularity container in there, and I know root's password. I can SU, right? Hit enter, type in the root password, right? Well, Singularity is going to obviously block that. We don't want to allow that sort of thing to happen. So it uses a kernel feature called set no new privs. It's a PR control system call. And we can block any privilege escalation from within the container. So a user calling this from outside the container, let's say I'm GMK outside the container, I spin up a container, I'm GMK inside the container, I have no ability to get additional privilege, even though I own that environment. And that's one of the reasons why it makes it so safe for high-performance computing resource centers to install and work with this. So this means that if you want to be root inside the container, you must first be root outside the container. And let me show you what that looks like. So is this the laser? Yeah. So you can see at the top of the page, who am I? I am me. If I do Singularity shell, by the way, if you haven't seen Singularity before, this is copy-paste. This is how you do it. It's very simple. Singularity shell, pointed at your image file, gives you an interactive shell within that environment. If I type in who am I, I'm GMK. If I type sudo who am I, now, of course you guys may not trust that I know how to install sudo. but I do, I promise you. I also know how to configure it, you know? I'm good at that. So, but you could see sudo is bombing out. It actually doesn't even know why. It just knows that, hey, I just ran, and my effective user ID is not the super user's. Why is that? I don't know. Go back, check your install. So we go back, do an ls -l on user bin sudo, and you can see it is, in fact, set UID, and it's owned by root. This should be working, but it's not. And that's because Singularity is blocking that pathway. And if we now call sudo in front of Singularity, this means we are calling Singularity as root. And as you can see, we are root from within the container. So this is a really important factor because, well, in HPC centers on shared resources, how many users have sudo privilege? Not many. You do? Oh, I thought you were raising your hand for a moment. I was going to say, they really love you.
Now, just a second. So that one of the reasons why containers are so popular is because you can have your own environment, and then you don't have to go to the system admin in order to install this package that you really need.
Oh, you know, I should have paid you for that one, because that's my next slide. Perfect segue. So here is the Singularity workflow. It does involve a system in which you own, but I'm pretty confident that everybody in this room has at least one computer that they can run on. A laptop. You can probably get an Amazon instance. You can probably get a workstation somewhere. We all pretty much have an endpoint. If you don't, come and talk to me later, and I will find one for you, let you borrow one. But basically, this outside box is a user endpoint. And this is the Singularity workflow. Basically, you're going to start with the sudo command, because we do need to be root to do system administration, whether it's on a container or whether it's on your physical host. So sudo singularity create your new image. This will create an empty image. Then we basically can import an image operating system. In this case, we're importing from Docker Hub. I'll talk more about that in just a moment. Or you can bootstrap, which means you're going to create a container image from scratch. Singularity comes with various tools and utilities to help you build operating systems. And then from there, you can interact and modify. So for example, sudo singularity shell, we're going to basically ask Singularity to mount this writable so you can make changes to it, and then point it at the container image. And once you do that, you can do apt-get install, you can do yum install, you can make any changes you want. There's no need to rebuild your image from that. All the changes are immediately persisted. And then you take that container image that we've created, and we copy it over to a shared resource which you do not have root on. You control this environment, the container image. You're not able to control it on this endpoint. So if you do need to make changes to it, you've got to go back over here and resynchronize. But that is a reasonable part of the workflow, considering you don't have the ability to make changes here, but you do have the ability to use this environment, just like you can do on the host. So here are the examples of running the container. Singularity run container.image. This will run a predefined workflow for that particular container. Singularity shell will give you an interactive shell. Singularity exec will execute or exec a program within your container, or a workflow or a script, or it'll execute something within your container. Okay, so just to make sure that everybody's cool with the workflow, again, we're going to go metaphors here. So sudo singularity create, boom, we have a new empty container. Sudo singularity bootstrap, we're going to put a whole bunch of stuff into that container. We now have a container that we love and we're happy with, and we can now copy that to other hosts. Doesn't matter what Linux it's running, as long as it's a Linux and it has Singularity installed. To different resources, your HPC compute resources that are provided to you, or Amazon or Exceed resources. And you can know, even if you're landing on a Debian system, this will work if you bootstrapped a Red Hat system, because the etc Red Hat release is inside the container. It doesn't matter where you bring it, you're always going to be running in the same environment. Okay, let's take a look at some usage examples. I'm going to come out here a little bit. Hopefully I don't get any feedback. All right, so starting from the top, Singularity shell, pointing it at the image. We're going to get an interactive prompt. If we type in uname -a, by the way, can everybody see this okay? Okay. If we type in uname -a, you'll see we're getting the expected results. Notice that this is a, well, the host name is CentOS 7, and we're running on an EL7. We're running on an EL7 kernel. So this is a Red Hat kernel, but this is a Debian container. and this is going to work just fine. If I do technical difficulties. So if we do a who am I, you'll see again I am GMK. Earlier I mentioned that Singularity is going to blur the line between what's in the container and what's in the host. And it does this so you can make efficient use of any resources and data that exist on the host itself. So in this case, Singularity automatically mounts my home directory and makes my home directory available inside the container. So what you can see is I can CD to a directory I have inside my container. And what I have inside this directory is the Git source code for Singularity. So I CD into that directory. And then if I do a configure, this is where now it gets a little weird. What am I configuring? I'm configuring Singularity, but what operating system am I building it for? It's not Red Hat. So even though I'm on a Red Hat host, I'm actually building Singularity in this case for Debian, because that's the operating system, that's the tool chain that I'm using. Now, this fails. And it fails for an extremely simple reason and an expected reason. I have not installed any compilers or development tool chains into this container. So from the configure script perspective, there's no C compiler. So this is the exact appropriate result that we should be expecting from this. OK, let's take a look at some Python. I wrote a hello world script in Python. I don't do much Python development, so this is about the extent of my Python work. I don't do very much Python development. Singularity is mostly in C, and the Python that is in it is contributed by somebody in this room who I'll point out in just a little bit. I wrote a hello world, so I mean, that was a big step for me, by the way. OK, so hello world, and it reports what version of Python is actually executing the hello world. And so what you'll see is on the host, I'm using the host version of Python, it's 2.7.5. Now inside the container, I don't have Python installed yet. With one command, sudo singularity exec, I'm going to make the container writable, point it at the image, and then I'm going to say apt-get install Python. Yes, it's that easy. And it will basically give you all of the apt-get output, and it'll say, you sure you want to continue? Yes, hit yes, and now you've got Python installed inside your container. So now I'm going to do a singularity exec, pointing at the image, and then what I'm executing is Python that exists inside this image. It's the Python we just installed even. Now the really interesting thing is that I'm running a script outside the image. And that's again because Singularity is blurring the lines between what is inside the container and what's inside the host. This is a feature. And as a result, the Python here is able to interact with the Python script that's outside the container. And again, you're going to get the expected result. In this case, we're running 2.7.12. Just to show and prove that pipes are also supported, I can cat hello world, pipe it into Singularity exec, and Singularity will redirect all of the standard input into the binary you're execing. So again, you're going to get the desired and expected results. Here's an MPI example. Now, this alone I can talk about for about 3 to 4 hours, probably more. But I'm going to try to keep this really brief. Now, first notice that this is a hybrid example. We have an MPI program inside the container, and we're launching it with MPI run outside the container. Now, anyone who's done MPI work on a big scheduler knows that there is a relationship between the MPI that runs on the host and the resource manager. The resource manager basically passes the environment information to the MPI. So you actually don't even have to give it any arguments. MPI will automatically, if everything's been compiled properly, MPI will automatically be able to communicate with the resource manager. So in this case, being able to use the host's MPI run is extremely important, because this means that we don't have to deal with coming up with host lists. We don't have to deal with passing any information through the container or wondering where those containers are going to end up on the network and how to get those IP addresses before they even exist. I mean, there's a lot of complexities if you do this in any other way, aside from exactly the way it was designed to do. So Singularity uses the way that it was designed to do. So basically, we're calling MPI run. This MPI run communicates appropriately with the resource manager that's running on your compute resource. Singularity exec, pointing at the image, and we're execing the MPI program. Now, the MPI program is going to run inside the image. When it runs, it's going to link against its local libraries, its MPI libraries in particular, inside that image. Those MPI libraries, now let's talk in OpenMPI, because that's where I'm most familiar. So in OpenMPI terms, those OpenMPI libraries are going to want to reach back and contact the original calling MPI run, or more specifically, the daemon that MPI run invokes, which is the ORTED daemon. So it will try to reach back and contact that. That communication pathway reaches through using, with OpenMPI 2 and newer, is using the PMI and PMI-X pathway. And that goes right through Singularity. So what this means is that you're calling MPI run on the outside of the container. Singularity is going to build a container for every process that you're running within your MPI world. It will invoke MPI ring. MPI ring then will be able to reach back and contact MPI run, and the job will proceed as it is designed to proceed. And this is very important because we have not hacked the MPI workflow at all. This is exactly what MPI expects to do. We've just interjected a container. Yes, question?
So you said before that your image can be from a different flavor of Linux. So how do you rectify something like this if you're running, say, a heavy image hosted right now?
So it's a really good point. Containers are never truly absolutely portable, especially when you're doing much more complicated things that do rely on things like host libraries. So the PMI link, so again, I'm going to talk in just in OpenMPI terms. All the MPIs are kind of handling this a little bit differently. But in OpenMPI terms, there's the PMI-X link. Now there is a version handshake, thanks to basically what I've articulated to the other OpenMPI developers. There's a version handshake along the PMI-X link. So it doesn't matter if you're using Debian in a container or SUSE or anything else, as long as the host version of OpenMPI, or more specifically PMI-X, is newer or equal to what's running in the container, the handshake can proceed just fine, and it works just fine. If it is not newer, you're going to get an error.
So how many things other than OpenPMI have that ability?
I can't tell you only because I don't do much work with the other MPIs. If there are any other of the MPI developers here, I apologize, you can kick me later. But I am most familiar with OpenMPI. We are working through the MVAPITs right now. Yeah, in a nutshell, do you have a moment to speak on how would MVAPIT deal with a situation like this?
We have a similar, like,
Can I ask, I'm sorry, can I ask you to come up to the mic? I can kind of hear you, but I'm not sure everybody else can.
Yeah, I mean, so we have a similar design like MPI run RSH, which spawns the processes. So what is happening is that spawn is happening, but with the Singularity, the things are not coming back to the main MPI run. I think that is the issue.
What about different versions? If there's a different version of MVAPIT inside the container versus out?
We have tried all these things, so I think we can discuss offline.
Okay,
Yeah,
okay.
we can
But
discuss.
in general, does it look like it's a reasonable problem to solve?
I mean, so we have been, I think, I don't know whether you or somebody else in your team, we are continuously discussing. We have posted something onto your mailing list.
Right.
I think that is the thing, that's the last mile kind of things we are holding on. If that gets resolved, then we can support Singularity also.
And I'm pretty sure we're going to be able to solve that problem. It's just a matter of finding, I think it's a file handle, keeping it open. But we will talk more. Yeah. Okay. I want to mention that there are multiple Singularity container formats that are available. So far, I've been showing you the default image format. There's also SquashFS. You can use tarballs as your image. Tarball does require caching, so expect a little bit of a cost associated with the caching. 5 minutes? Okay, I'm going to go really, really fast. Okay. Network images are also supported, like Docker, HTTPS, and Singularity Hub. So here's an example of using the Docker interface. So instead of pointing it to an image file, we're pointing it to a Docker API. We do not have Docker installed on this host. And it's able to basically pull the latest version of Python out of Docker Hub, and we do an exec to user local bin Python, point it at the hello world script. Now you can see we're running 3.6.0. One more example that I want to show, sorry for the small type, is now we're basically pulling TensorFlow. This is a host, obviously doesn't have Docker installed, and it doesn't have anything to do with TensorFlow on it. And we're able to run, basically, with one command line, we're able to download the TensorFlow image out of Docker Hub. We're able to run it, and we're able to basically do an example model. Some information about performance. Containers are much more performant than virtual machines in general. Singularity is even more performant because it has a very light footprint, and we don't isolate all the processes. So the number of namespaces that we utilize is actually very small in comparison to Docker, which utilizes all of the namespaces to try to achieve full isolation. And this basically ends up with some performance impact. So some cases you can see that there's no performance impact. Blue is Singularity, green is native, and red is Docker. But you can see in some cases we have a much bigger spread of where the performance impact is. I don't want to go into this in too much just because we don't have time. This is MPI shared latency through OpenMPI running different containers. If isolation was utilized and we were separating out the VM namespaces, we basically wouldn't even be able to do this because you'd have to basically, if you can't do shared memory between containers, you have to go out to the network to do that communication. In this case, we're basically mirroring host performance until we get to very large packets. And this is a really interesting graph. CentOS 7.2 is running native. CentOS 7.3 is running in a container. And you can see we're actually getting lower latency across InfiniBand. And this is not, we're not testing the overhead associated with a container. We're testing the libraries inside the container image. So we actually have a more performant library of the InfiniBand library here than we do here. And you can see that relates to a specific performance increase. And I also don't want to lie to you guys. Notice that the scale doesn't go down to 0 in either of these. So we're just looking at the very tops of the graphs. It's a little misleading. Taste for things to come. Singularity greater than version 2.2, whereas what we're at right now. We're going to have data containers, be able to do more without privileges, capture changes and support for background processes. Sorry, I'm trying to go really fast because the coolest thing that I want to show you guys is Singularity Hub. So Singularity Hub is a container registry, and it is built and designed by Vanessa here in this room. Raise a hand. She's here at Stanford, and she's doing amazing work on this. And I'm going to jump to, you can see some screenshots, but I'm going to jump to this. For everybody who has a research project, let's assume that we got something in GitHub. You can basically drop a Singularity Bootstrap definition file inside your repository in GitHub, link your GitHub account to Singularity Hub, and every time you do a push, it will invoke a continuous integration to rebuild or to create a container for your project. Now this container gets integrated with Google Cloud, and it now becomes available via the, I showed you some of the screenshots, but I went really fast. It becomes available to be used by other people. Now the end goal of this is because we want scientists to cite in their publications the containers that they're using in order to create their workflow. So this is really looking at reproducible work and taking it to the next level and making it as absolutely brain-dead easy to reproduce work as possible. So when you are publishing documents, include the unique ID for your container. Anybody can then come along that has Singularity installed and with one command recapitulate or leverage all of the work that you've already done for a particular project or proposal or publication. So to me, this is just taking everything that Singularity encompasses and the design of Singularity and the motivation of Singularity and puts it all into one thing where we're basically handing it back to the scientific community and asking for the scientific community to work with us and to get this exactly where we need and then utilize it. Because, you know, reproducibility is an incredibly important thing. And I'm not sure why it's just getting all the attention it is now. It should have always been there. But right now, we're getting a lot of attention on reproducible science. This is a huge facilitator for that. Earlier, I mentioned it's developed for scientists, by scientists. This is not the users. These are the contributors. These are the people that have taken part in investing their own time and energy into creating Singularity. It is licensed BSD. It's completely open source. Everybody can go use it, contribute to it, help us. We are overwhelmed with all of the work and everything that's coming at us. So please join, help us. Let us know what we're doing right. Let us know what we need to do better. And again, yeah, Singularity, because I like the image. Yes, questions?
Yeah, hi Greg. I would like to plug the talk about the Linux containers tomorrow, because I think...
Oh, come to the mic.
Yeah. I won't spend too much time, but I would like to plug the talk of tomorrow that I'm giving about the state of Linux containers, because I think some things you said are a little bit misleading, maybe. So, I mean, you compare Docker, not run C, so you compare a runtime and an orchestrator, so I think that's a little bit misleading. But I think we should talk. Definitely we should talk.
We can debate it, and we can even, you know, have like, you know, people betting on us. And
yeah.
it'd be really cool. It'd be really cool.
Yeah, so...
If somebody wants to pay for my ticket, maybe.
So we should have a talk. I mean,
okay,
pretty cool.
Definitely,
Thanks.
definitely. And good to see you again, Christian.
Yeah, sure.
Even if you're challenging me, it's still good to see you.
That's what we do, right?
Yeah. Are there any other questions? Yes?
Could you modify, because at least the way it's right now, it seems like it won't be applicable to the microservices, because you can't say install a web server in your image and then run two instances of that container, because they'll both try to open the same port and die,
yes.
Right? Could it be modified to support microservices?
So I don't like talking about this because I don't want to appear as if I'm going after Docker's use case. I'm not. But I will say this. There are a lot of use cases that are specifically for scientific computing that do require service virtualization. And how to actually do that, we have been thinking about. When I was talking about the features of what's to come, background processes was listed there. But you're right. It's something we're thinking about. It's something we will integrate at some point. I don't know when. But again, I'm very... I don't want to conflict with the Docker use case. I think they have a great solution, and I don't want to step on their toes. So with that said, eventually, yes, we will support background processes and service daemons. Are there any other questions? Yes?
Can the creation of these containers be kind of integrated with the queuing system of any kind?
So yes, there's no dependency whatsoever on the queuing system. There is some work to create a module for Slurm, a Spank plugin, that will automatically build the Singularity container environment and integrate closer with it. But there's nothing required. A user would just type in this, just run the Singularity commands within their batch script. It doesn't matter what resource manager. If you want to follow on Twitter, GitHub, or Slack, please just send me an email for an invite for Slack. Otherwise, here are the links. Thank you very much. I will be here for a while longer, so please feel free to ask me anything. Thank you.